Suppose A and B are 2 points having the position vectors A vector and B vector, respectively. C is a point that divides AB internally into ratio m is to n. The position vector of the point C will be given by mb vector plus na vector over m plus n. Okay, let's try to prove this. So here what we'll do, we'll consider 2 points A and B. Also we have a point A and then we have another point B. Now what we'll do, we'll consider a coordinate system. Now, in order to define the position vector A and B of the point A and B, all we have to do is draw a directed line segment joining points O and A going towards point A. This is going to define the position vector A. Similarly, to define the position vector of the point B, all we have to do is draw a directed line segment joining the origin and the point B with the direction going from O towards B. So we have the position vector B. Now our goal will be to join point A and point B with a vector going from A towards B. Now let's say we have a point C on the line AB, and this particular point C is dividing the line segment AB in the ratio m is to n internally. Now our goal will be to define the position vector of this particular point C. In other words, we need to show that the position vector OC is given by this particular formula. Okay, let us begin. Now, since the point C divides AB in the ratio m is to n internally, we can say that we have the ratio ABAC to that of CB that will be equals to m is to n. Let this be number 1. Now let's cross multiply to get n times AC. That will be equals to m times CB. Now, since we want to work with vectors, so what we'll do, we can simply vectorize them. So we have A towards C, to get the vector AC, since we're going from A to B, and then we're going from point C to point B, so we have the vector CB. Fine. Now, how do we define the vector AC in terms of the position vector? So to define AC vector, all we have to do is take the position vector of the head. So the head will be the position vector of C. We're going to call it OC vector. Minus, we're going to take the position vector of the tail. So that's simply A vector. So we have OA vector. That will be equals to m times. So CV vector will become OB vector minus OC vector. Where, let's write it down, where OC vector is the position vector of the point C. Fine. Now, let's further simplify. We have n times OC vector minus the OA vector. So here OA vector is simply the vector A. So we have OC vector minus A vector equals to m times and OB vector. The OB vector, the position vector OB will be defined by the vector B, where B vector minus OC vector. Let's further simplify to get n times OC vector minus n times A vector. That will be equals to m times B vector minus m times OC vector, which will be equals to, now we need OC vector. We have n plus m times OC vector. That will be equals to NA vector plus MB vector. Now, further simplification is now going to give us, we have OC vector equals to m times B vector plus n times A vector divided by m plus n. Now this is going to be the position vector. This is the position vector of the point C. Okay, let's verify. Yes, it's MB vector plus NA vector over m plus n. If we have a point dividing any vector internally, then the position vector of that particular point will be given by this particular formula. This is called the internal division. Now let's go to the next theorem, which will be external division. Now, if we have A and B being 2 points with position vectors A and B respectively, and C is a point that divides AB externally into ratio m is to n, then the position vector of that point C will be given by this particular formula. Okay, let us begin. First, let's try to understand it graphically. So here we have the coordinate system. It's a 2-dimensional coordinate system with the origin at O, and we have 2 points, point A and point B. Now the position vector of point A will be A vector and the position vector of the point B will be B vector, which is simply the vector OB vector. Now we're going to consider a third point C. Now C is going to be chosen such that if we extend AB, then we have this particular point C. Now we will suppose that this C point is going to divide the line AB in the ratio m is to n externally. That means AC, the length AC is going to be m. As we can see here, the point C is dividing AB into ratio m is to n externally such that AC has a length of m units and BC has a length of n units. Fine. Now we want to find out the position vector of the point C. Now clearly it's given here. In our problem we have assumed C to be such that C divides AB in the ratio m is to n externally, which means that we have AC over BC, so that will be equals to m is to n. Fine. Now let's now cross multiply. The cross multiplying gives us m times BC, that will be equals to n times AC. And we want to convert it to a vector. So we have the vector BC going from point B to point C, and we need AC which also goes in the same direction as that of BC. So we have n times AC vector. Now let's open up the vector BC in terms of the position vector. So we have OC vector minus OB vector. So that will be equals to n times OC vector minus OA vector. So that will be m times OC vector minus m times OB vector. That will be equals to n times OC vector minus n times OA vector. Fine. So we now have m minus n times OC vector, that will be equals to m times OV vector minus n times OA vector, such that OC vector, that will be equals to m times OB vector minus n times OA vector whole divided by m minus n. So here, this is the formula for the external, this is the position vector of the point C such that it divides AB into ratio m is to n externally. So let's try to understand both of the two theorems with the help of a few examples. Example number 1. We need to determine the position vector of the point dividing the joint of the point, these are two vectors, internally and externally into ratio 2 is to 3. Okay, let us begin. So here, let A and B be 2 points such that the position vector of the point A is given by OA vector, which is simply equals to the vector 2A minus 3B vector. Then we consider the position vector of the point B. Let's call it OB vector. So this is defined as 3A vector minus 2B vector. Okay, to understand this problem, what we'll do, we'll choose 2 points. So let's say this is the point A. So A has the position vector 2A vector minus 3B vector, and then we have now the point B. B has got the position vector defined as 3A vector minus 2B vector. So here we will be considering a point C such that C divides the joint of A and B internally in the ratio 2 is to 3. Fine. Now our goal will be to find out the position vector of this point C, meaning we need to find out OC vector. Now OC vector will be, all we have to do is consider this value 2. The 2 will get multiplied with the 2 will get multiplied to the position vector of OB, added to 3 times, so 3 will get multiplied to the position vector of OA. Now we have 3 times OA vector divided by 2 plus 3. Fine. Now what's OB vector? So that's simply 3A vector minus 2B vector added to 3 times we have OA vector. The OA vector will be 2A vector minus 3B vector whole divided by 5. Okay, so let's further simplify this. So we have 2 times 3, that's going to be 6A. And here we also have 3 times 2A vector, so that's going to be 6A. So 6A vector plus 6A vector will be 12A vector. Then we have negative 4 vector minus 9 vector, so that's going to be negative 13B vector. So divided by 5. So this is going to be the position vector OC such that C divides AB in the ratio 2:3 internally. Now let's find out how when the point C divides the join of AB externally. Now this time the point C divides the join of AB externally in the ratio 2:3. Now we have to be very careful where we choose the location of the point C. Now there, in this particular case, I am choosing C to be near to A. That's because it's given here that C is dividing AB into ratio 2:3 external, which means that AC is going to be 2 and BC is going to be 3. Fine. So therefore, now we can apply the external section formula, which means we now have OC vector. This is going to be defined by, so we will take 2. 2 will get multiplied with the position vector OB. So we're 2 times OB vector minus 3 times OA vector divided by 2 minus 3. So this will be equals to 2 times. So what is OB vector? So that's 3A vector minus 2B vector minus 3 times we have OA vector. So OA vector will be 2A vector minus 3B vector divided by negative 1. So we have 2 times 3A, that's 6A vector minus 2 times 2B vector will be 4B vector minus 3 times 2A will be 6A vector. The negative 3 minus 3B vector will be positive 9B vector divided by negative 1. So 6A vector and 6A vector cancels out. We have 9B vector minus 4B vector, that's positive 5B vector, but we have division by negative 1, so we have negative 5B vector. So this is going to be the position vector OC such that C divides the join of AB in the ratio 2:3 externally. The second example, we need to determine the position vector of the points trisecting AB, where A vector and B vector are the position vectors of the points A and B respectively. Let us begin. We'll try to understand the problem graphically first. Let us consider 2 points A and B. And it's given here that these 2 points A and B have the position vectors A vector and B vector respectively. Let's join point A and point B with a directed line segment going from A to B. Now we're going to consider 2 points P and Q. Now P and Q are chosen in such a way such that AP will be equals to PQ and this will be equals to QB. In a sense, we can say that P and Q are trisecting AB into 3 equal parts. Now, in order to solve this problem, let us suppose that AP equals PQ equals QB, and that's equals to lambda. So first, we'll try to find out the position vector of OP. Now, it's clear that P divides AQ internally in the ratio lambda is to lambda. Let's join point O and point P. That means let's define the position vector OP. Now clearly we can see here that point P divides AB in the ratio lambda is to 2 lambda internally, which means that we can now define OP vector. The OP vector will be, let's take lambda and multiply with it B vector. We have lambda times B vector added to, now we'll have to take lambda plus lambda, so that's 2 lambda. So that means we are taking PB, which corresponds to 2 lambda, and multiply it with A vector divided by lambda plus 2 lambda. So here we can factor out lambda from the numerator and the denominator, leaving us with B vector plus 2A vector divided by 3. So that means that is the position vector OP, which divides AB into ratio lambda is to 2 lambda. Now let's join point O and Q to get the position vector OQ. Now this time Q is going to divide AB internally in the ratio 2 lambda is to lambda, which means we can define OQ vector as well. So OQ vector will be, we'll take lambda and multiply it with vector A to get lambda A vector added to, now we'll have to take 2 lambda and multiply it with B vector to get 2 lambda times B vector divided by lambda plus 2 lambda, and that's going to give us we have A plus 2B vector divided by 3. So therefore we have successfully obtained the position vector of the point P and point Q such that these 2 points trisects the line joining A and B, whose position vectors are given by A vector and B vector respectively. Let's do one more problem. Now we have three distinct points A, B, and C. And each of these 3 points have the position vectors given by A vector, B vector, and C vector respectively. Now, there exist 3 non-zero scalars x, y, and z such that x times A vector plus y times B vector plus z times C vector, they adds up to give us the 0 vector. And also, if we sum up these non-zero scalars, then that sums up to give us the value 0. We need to show that the 3 points must lie on a line. That means if these two criterions are met, then it must be true that the 3 points are collinear. Okay, let's try to understand the problem first. So here it is given here that we have xa vector added to yb vector plus z times c vector equals to 0. Now this is defined for 3 points A, B, and C. Now point A, point B, and point C has a position vector A, B, and C respectively. That means we have some origin O. So if we join point O and point A, then we get the position vector A. Joining point O and point B gives us the position vector B. Joining point O and point C gives us the position vector C. We need to show that A, B, and C, these 3 points lie on a line. So that means if we draw a line, then these 3 points must lie on that particular line. Now let's try to rearrange the terms. So here we will keep z times c vector on the left hand side and transpose the first 2 terms on to the right hand side to get xa vector added to yb vector. Now we can divide by a scalar. So we have c vector equals to negative times x times a vector plus y times b vector divided by the scalar z. But it's given to us that x plus y plus z, that's equals to 0, which implies the z must be equals to negative of x plus y. So if we substitute this, then c vector, this implies that c vector becomes equals to x times a vector plus y times b vector divided by x plus y. Now, this particular relationship tells us that C, the point C, you can say the point C divides the line joining AB in the ratio y is to x internally. So this is the formula for internal division. So if they're dividing it internally in the division y is to 6, that simply tells us that this implies that A, B, and C must lie on a line. In fact, if we go to our figure, so actually C is going to lie between A and B. So let's redraw it. So this is going to be point C and this is going to be point B. So we need to change the position vectors as well. So here we have C vector lying between A vector and B vector. So here this is dividing it in the ratio, since we have x times A vector. So this is x and this is going to be y. So we have C dividing AB in the ratio y is to x internally.